Hello class, today we are going to have isoparametric bar code. So a bit more advanced than previous workshops. Let's start with the title, which is going to be an isoparametric bar. First, let's clear everything. Otherwise, we are going to have some arrays or matrices from the previous simulations, which we don't want it. And then we need to know what problem we want to solve. Let me show you the problem. This is the problem we want to solve. 1 bar, 2 ends, which is going to be node 1 and node 4, they are fixed. So no displacement at node 1 and 4. Definitely we are going to have 3 elements. At node 2 we have this force, which is 3000. And the distance between these nodes are, all of them, they are 30. So they are equally spaced. Let's write the code, the material properties. So Young modulus E is going to be 30 times 10 power 6. Then let's write a title for this. Problem parameters. The next one is going to be cross-sectional area. Let's make it simple, 1. I'm going to define another parameter as EA, because everywhere we are using Young modulus, we are going to have cross-sectional area. So EA is going to be E multiplied by A. So we take care of that part. And the length, let's consider it's 90. Now, what is the number of elements? Number of elements. So the parameter for that is going to be number elements, which is 3. We assign this number of elements. Then for this calculation, we need to know the position based on x. For example, what is the distance of node 3 from the left side, which is going to be 60. What is the position of node 4? It's going to be 90. So we need to have a line spacing between these nodes. So generating equal space between nodes. So to do that, I'm going to define a parameter node coordinates, which is going to use line space from 0 to L, and give me number of elements plus 1 point between those two numbers, 0 and L. So basically, I said between 0 and L, which is 90, give me 4, because number of elements is 3, 4 points, equal space points. So it is going to be these 4 nodes. Okay, beautiful. And let's save this coordinates, node coordinates inside XS. Later I'm going to use it for other calculations. So now number of nodes, so I think yeah, we use this method, which is finding the size of an array to find the number of nodes. So size of node coordinates is going to give me the number of nodes. But this number of nodes, we need to know what type of array is that. Is it a line matrix or column matrix? So I don't know that. So let's check it. First save. Okay. I'm going to stop the code here. What is... oh yeah, because I haven't finished. So let me finish this. Stop it here, save. Line. Oh, dictation mistake here, line space. So save it, run. Now I can see. This is our Young modulus, EA, same as Young modulus, L, the number of elements, now coordinate. Okay, now I know it's a one row with 4 columns. So here, when I want to get the number of nodes, I need to check this size. So I need to get back the number of columns. That is why I'm going to do this. Give me the second dimension. Because this is 1 by 4. I just want the 4. So I use this 2 to give me the second dimension of the matrix. Now, element connections. Element connections. Okay, this time I'm going to do something else. So let's define O is going to be from 1 to number of elements, because I need to repeat 3 times. And define these connections, element nodes, in a way the first one, the first column is going to be O, and the second column is going to be O plus 1. Now, basically, I'm constructing a matrix for connections, which is the first column. First column is going to be, for example, because O is going to start from 1, this is going to be 1, the second column is going to be 2. Then O is going to be 2. The first column is going to be, in the new row, the first column is going to be 2, the second column is a 3. So basically, 1, 2, 2, 3, 3, 4. So I can easily construct this connection matrix. Now let's define displacement and forces and stiffness matrices. So we are familiar with this one. Displacement is going to be all zeros, and the size is going to be number of nodes. Where is number of nodes? I don't want to write number of nodes. And 1, because it's supposed to be column matrix. Let's copy this here. This time this is going to be force. Same column matrix. Again copy here. Stiffness. It is going to be n by n. The number of nodes by the number of nodes. Okay. Now we have all the matrices we need. Next step, let's apply the boundary conditions. Apply force. So force at some node supposed to be 3000. So let's go back to the picture. So for node 2 we need 3000. So second row I need to have that force. Now it's time to construct stiffness matrix. Stiffness matrix. Okay. I hope you remember what we did in the lecture, how we construct stiffness matrix. Let's review a few points and then I'm going to come back. When we had ISO parameters, we defined this psi parameter from negative to 1 to 1, and we converted all the global coordinates, which was x, to this psi, which is the natural coordinate system. And we said, for example, for displacement interpolation, which we said we may be able to write that displacement u or d, whatever the name is, we can write it in good approximation as a n1 times u1 plus n2 times u2, and so on, depends on the number of nodes. n1 or n2, or they are shape functions. And basically they are a formula in terms of x or natural coordinate system, this psi. It can be a line, it can be a second order, third order, quadratic, cubic formula to have a better approximation of this u. u1, u2, u3, they are local displacements at that node. For example, here we have 3 nodes, node 1, node 2, node 3. These u1s, u2, u3, they are the displacements there. And then we did some calculations. We found out that B matrix here is going to be the derivative of shape functions. If we are using isoparameters, derivative of shape functions over psi, in terms of psi. If we are using global coordinate system, this shape function's derivative is going to be with respect to x. And you need to multiply with Jacobian, inverse of Jacobian. What was the Jacobian? Jacobian was the derivative of global coordinate system over local or natural coordinate system. And for 1D case, which we are working now, if you find derivative of x is going to be n times x, and derivative of x is going to basically derivative of n times x, because x1 and x2, they're not dependent on the coordinates, this size, natural coordinates variables. So, but in 1 and 2, they have their formula, they have this psi. And if you're looking for the formula, this is the formula for example, linear case. So you find derivative for the n1 is going to be negative half, derivative for n2 is going to be positive half. We put it here, so Jacobian is going to be negative half, positive half times x1, x2. And if you multiply these two matrices, you are going to have x2 minus x1 divided by 2. x2 minus x1 is going to be length of that element. Sometimes people put L, small e here, to show this is about the element. So half of the element length is going to be Jacobian. And if you want to find determinant of the Jacobian, because here for 1D, Jacobian was in one number, the determinant of the Jacobian is going to be again this number. Okay, so now we found Jacobian. We put here the inverse of Jacobian times derivative of the shape functions is going to be B matrix. And then you need to plug all the numbers here. Transpose of B matrix times B matrix times determinant of Jacobian. Here for 1D is going to be exactly the Jacobian, so half of the length, times weighting function. If you want, and you already know, I showed you some tables, how we can find. If you want to find the point you selected is at the center of the element, which is going to be psi equals 0, this W is going to be 2. If you go, for example, psi equal 1 over 3, square root of 3 or others, this W is going to be different, and A multiplied by AE. And you need to do the summations of all of them for the all elements. So I1 to n is going to be for all the elements to construct this K matrix. I'm going to now write the code for this procedure. Okay, let's write a for loop. E from 1 to number of elements. It's a good idea to always copy it, because if you type it again, you may make a mistake, and later finding the mistake, it would be difficult. So I don't need that. Now I need to extract the connections, similar to the code we did a few sessions ago. So element degree of freedom, or the connections for the first element, is going to be, where's element nodes? I saved it somewhere here. These are the element nodes supposed to save the connections for each element. So I'm copying this. So I'm looking for first row. So E here is 1. So first row, everything, all the columns. So first row is going to be saved inside degree of element degree of freedom. Excellent. And then let's find out what is the length. And I'm going to save this length of this degree of freedom here. Whenever you have a question about a function you don't know, you just need to right click and click help on that function. For example, for the length, it says returns the length of the largest array dimension in the array inside that length. So for this case, element degree of freedom, it's 2. We have just 2 points inside. If we had more points, you can extract that, for example, the number of points we have using this. Okay. Now, because in this formula, let me show you. Because in this formula we have L, or the length of the element, I need to know what is the distance between, for example, what is the distance between node 1 to 2. So I need to subtract the x of node 2, x of node 1 from node 2. X for node 1 is 0, this one is 30, so it's going to be 30. So, length of element is going to be, where is the node coordinate? I already adjusted that, so node coordinate of this minus node coordinate of, again, some point. Now let's decide which points I want to know. I know up to this stage, let me stop it, save it, and stop it here. Yeah, I need to finish this line and then be able to check it. Let's write this and then later I'm going to explain. Oh yes, I haven't ended this. So let's end it. Hopefully this time it's going to stop. Okay. Now this is element nodes 1, 2, 2, 3, 3, 4. These are the connections we saved where? Here. I saved the connections. You could do in many ways. I decided to use something new, so this is the way I saved the connection. It's much more compact. So this element nodes save the connections between elements. Now, element degree of freedom is going to extract one by one those lines. So let's go one step further, and this n is going to be 2 because length of this has just 2 elements inside. Okay. Length of element, I want to find the coordinate of this second element minus the first element. So that is why I said coordinate of the second one here, which is the second node, minus element coordinate of node, the first one, which is the node 1. So in this way, I can find the length of the element. Okay, let's do some, for example, determinant. Determinant of J is going to be, let's go back, because Jacobian was length divided by 2, and it's a one number, it's not a matrix, so the determinant is going to be same number. So determinant is going to be the length I just found divided by 2. And inverse Jacobian is going to be 1 divided by this Jacobian. So we took care of those things. Now I need to find B matrix. B matrix has two components. The first one is derivatives with respect to natural coordinate and inverse Jacobian. First part, inverse Jacobian, is done here. We found it. Now I need to take care of the derivative of natural coordinate. So to do this, I'm going to write a separate function, because if I write it here, it is going to make it crowded. So let's call a function and write that function. So I want to have a function with which is going to return two parameters, shape. Later I'm going to tell you what is the shape. And natural derivatives. So my function is going to return these two, and let's name this function shape function 2 for just 2 points, because we have different types of shape function which they can have many points, sampling points inside. So this is going to be a specific case of when we are going to use just 1 point inside the element. So the sampling point is going to be 0 at the center of element. Okay, and this is our function. Okay, let's write the function. So function is going to be shape and natural all the time. Natural derivatives, and this is going to be equal the name of shape function and the value here is going to be psi. What is psi? You remember psi is the natural coordinate for this 1D case. So this is our psi. What is this function is going to do? It is going to return this shape and natural derivatives. I don't remember the shape. Let's check the shape. So 1 minus psi divided by 2 is going to be n1 shape function. 1 plus psi divided by 2 is going to be the other shape function. So let's put the shape function here. Shape function is going to be 1 minus psi, let's have parentheses here, divided by 2, and 1 plus psi divided by 2. And this is row matrix. Let's find the vertical matrix there. Okay, now I converted this shape function to the vertical or column matrix. First one is going to be n1, the second one is going to be n2. Done. Okay, now I need to find natural derivative. Natural, copy always. Natural derivatives. So let's go back. Where is it? Here. The n1 over the psi is going to be negative half. The n2 over d psi is going to be positive half, which you can see. If you get derivative of n1, you get rid of this. This is going to be negative 1, negative half. This is going to be positive 1, so positive half. So just write it here. Negative 1, next column, positive 1, all of them divided by 2. So these are our derivatives. End. So here my function is going to call this function, and it is going to calculate my shape functions in a column matrix and natural derivatives, which I'm going to use it for constructing B matrix. Okay. Now I need to find this value. So this is B matrix. Inverse derivative times this matrix is going to be B. Let's do it. I'm not going to call B. Let's call it XD for now. Natural derivative, which my function calculated, times inverse Jacobian. Where is inverse Jacobian? Okay, done. This is my B matrix. Now let's construct B matrix. Strain displacement matrix. So B is going to be equal 0. First start with 0. One row and an n matrix nodes, and an n here is the number of nodes we have inside the element, which was 2. Why? Because we have 2 points, so your B matrix is supposed to have 2. Then I need to put the calculated values inside B matrix. So from 1 to an n, put the calculated values here. Okay. Now our B matrix is ready. Now let's construct stiffness matrix. Stiffness matrix. So K. Let's go back once more here. So K is going to be summation of these multiplied to each other for each element. So AE times W, which is going to be 2, determinant of Jacobian, we already calculated, half of the lengths, transposed of the B times B, and add to each other for each element. Let's do it. So where is the stiffness matrix? Here, Control C, Control V, stiffness matrix of the connections. I already extracted that connection, degree of freedom, element degree of freedom. This part is very similar to the other stiffness matrix construction, so I'm just doing the same. This is going to be equal. Again, because we are going to add for all the elements, I need to repeat this. plus, I haven't saved. Let's save this. Where are you? Now I can close it. Plus, let's write from end. So transpose B times B. B transposed times B W is 2 times determinant Jacobian times AE. So times 2 times, where is determinant Jacobian? Determinant of the Jacobian times AE, which I already put parameters just for AE. Done. Okay. Let's save it and run up to this stage and see what's happening. So this is, I could have stopped earlier. Let's stop, for example, here and then go there. So this is the lengths we had. Length of element for each element is 30. We know that. Determinant of Jacobian is 15. Half of the lengths, correct. This is inverse. Let's go the other one. Now it is going to call the shape function to calculate shape function. Half, correct. And for 0 point, it is going to be half. Why? Because if you put size 0 here, it's going to be positive half for both sides. So correct. And natural derivative, negative half and positive half, this is also correct. We explicitly assign that, so it must be that. And then B function, first line matrix, both 0. And then we put the values of the natural derivative times inverse Jacobian, which we calculated here, inside this. Basically, I just wanted to separate strain displacement matrix or B matrix from the rest of calculation. So I could just do the calculation inside here. Yeah, anyway. Then we constructed the stiffness matrix. This part is very similar. The second part is just coming from the formula, transpose B times weighting function. This weighting function can be different for the number of points you selected. If you have just one point at the center, which psi equals 0, this W is going to be 0. Check the tables in the lecture notes. Determinant Jacobian times AE. Excellent. Okay, now let's apply boundary conditions. Boundary conditions, basically I want to put the fixed values, because I know that fixed supports, they are going to have 0 displacement and I don't need to calculate for those points. So fixed degree of freedoms or fixed nodes, this time I'm going to do something different. Find XX minimum of, where is node coordinate? Node coordinates. So find minimum value of inside node coordinates. And also find maximum value inside node coordinates. And I want to have vertical or column matrix. Done. So basically, the question says this is our fixed coordinates, number 1 and number 4. What I said, find the maximum value here, this one, number 4. Find the minimum value of this one, save it in a column matrix. Or you can just say 1 and 4, I know that. Anyway, so this is going to be our prescribed degree of freedom. Let's put this here. And let's find the free one. Free nodes. Active degree of freedom is going to be equal set difference between 1 to number of nodes. Where are your number of nodes? Number of nodes. But this is a row matrix, make it column matrix, and the prescribed one, which is already column matrix. Why I did it here? So compare these two matrices, and the difference is going to be our active node. So let's go back. 1 and 4 is the fixed one. The difference is going to be 2 and 3. Now, solution. Okay, I can write a function for that, or just write the solution, whatever you prefer. Let's write function because it's a good practice for us. So let's write the function. Displacement. Where are you? We defined it here. Displacements, because the value is supposed to be displacement, and bring it back to us. The name of this is going to be solution 1, for example, this function, and I'm going to pass this number of nodes prescribed degree of freedom, stiffness matrix, because I need to calculate stiffness matrix, and forces, multiplying forces to stiffness matrix. Where are you? Here. That's it. So this is going to be the way I'm calling this solution 1 function. So function, so let's copy solution 1. It is going to give something. I need to write like this, displacement or any name, whatever function does, supposed to put it inside. Let's change the names. Number of nodes, smaller names. And then the second one is going to be boundary conditions. Third one, stiffness. Let's look at it as a K. And the fourth one is force. Okay. So I didn't pass this one. Let's write this here again. So because I need to calculate just for active nodes. So the number of nodes here, this is going to be boundary condition. So here I'm going to have the active nodes. Let's name it something. Active nodes. Okay, now I have active nodes here. Let's name this U equal stiffness K of active nodes So I just want to calculate for active nodes, backslash force of the active nodes. And then displacement supposed to be zeros. That size is going to be number of nodes and 1, so 1 column. And now put the values, calculated values inside displacement. Displacement of active nodes is equal U. We're done. Okay, let's save it. Done. Let's run. Okay. I would like to see displacement. It's going to be 0.002, 0.001 for node 2 and 3. The other must be 0, correct? For example, stiffness matrix. Let's see what is the stiffness matrix. This is our stiffness matrix, correct? And force, correct, because the only external force is 3000 there and the rest. Okay. Thank you very much and see you next time.